Hi there, my name is Patrick Dietrich. I'm the CTO here with ConnectTech, and today we're going to be talking about deploying powerful fog compute systems with integrated NVIDIA and Intel technology. Okay, I'm going to do a quick overview of the IoT AI data processing models. So you're probably familiar with cloud computing, and I'm going to look from cloud computing sort of as a top-down approach here. So cloud computing is typically done by big data processing in data warehouses, data centers. People are familiar with that. You would go up to the network, you go up to the cloud and access this data. So both edge computing and fog computing offer similar functionalities in terms of pushing both intelligence and data to nearby analytic platforms that are located either on or near to the source of that data, be it cars, motorways, speakers, screens, sensors, or pumps. Both the technologies leverage the power of computing capabilities within a local network to perform computational tasks that may have been carried out in the cloud easily. They can help companies reduce their dependencies on cloud-based platforms for data processing and storage, which often lead to latency issues and are able to generate data-driven decisions faster. So most people would be familiar with cloud computing and edge computing. Fog computing is maybe a lesser used term, and really it's meant to say that it's a point of computing to do the data analysis and reduction on a local network that will be directly connected to edge computing devices, but sits between the edge and the cloud such that the processing speed and response time is drastically reduced. So lastly, when we talk about an edge computing device, this is where the processing power is actually located directly into the device. So you could think of this as the sensor head, or where the cameras are located, is that the processing capability in this case would lie directly on that sensor or camera. So now we're going to talk about why fog systems would be used. So one of the biggest advantages of fog computing is that it reduces latency. Data doesn't need to be sent to the cloud in order to be processed. In cases such as vehicle-to-vehicle communication, latency becomes a matter of life and death. Centralized computing has proven unable to cope with provisioning resources to devices at the edge of large networks, and fog computing addresses those issues. This technique is used a lot to have it more of a distributed, decentralized processing capability to reduce the latency of fetching that data and pushing it up to the cloud, and then as well to achieve some of these real-time analytics that perhaps there may be more processing that's needed from the edge, but you don't have the time to go all the way to the cloud and back. That's where these fog systems come into place. In many environments, the ability to analyze data in real time is of paramount importance. Eliminating the inefficiency and latency that comes with cloud services means that the user can receive genuine real-time analytics. So now we're going to talk about where fog computing solutions are used in the field. The first use case I'm going to cover is a smart city application. Here you can see from this graphic, we're looking at an intersection where stoplights and stop signs eventually will become unnecessary in these roadways. So by monitoring the traffic in these intersections, can interface with upcoming vehicles to assign lanes, speed, and queue priorities, and keep cars moving without the risk of a collision. The edge devices in this application are shown in some of the cameras in the vehicles themselves, and they'll include some of their sensor payloads like RGB cameras, LiDARs, radar units, and the processing is held directly within this edge device. And some of the processors that are held within these edge devices are the NVIDIA Jetson platform, as well as some ARM and lower powered x86 platforms. The higher amounts of processing is done by the fog compute system, which would be held at the intersection utility server. And this would be collecting all the data from the edge devices and processing that in real time. And this takes quite a bit of computational power. These fog compute solutions can consist of higher performance x86 processors paired with discrete GPU accelerators, and they're thermals designed such that they can live in these outdoor environments. these would be typically systems that can still be small enough form factor that they can still fit, but that don't need to be so big that it would be a big rack mount server. So these leverage a lot of different technologies, but harness some of the latest generation NVIDIA GPUs from the NVIDIA Quadro series. Finally, when things can go back to the cloud, to services like AWS or Azure, these are sort of at the last leg for more of a data collection and sort of low-speed processing that don't require these real-time aspects. So why fog was a better solution here was there's just simply too much horsepower to put within the camera itself and in the edge devices. And these real-time decisions are needed for safety. So in this application, you can't rely on cloud bandwidth constraints to make these decisions in real time. The next use case I'm going to discuss is where fog computing can be used in an ISR application for intelligence, surveillance, and reconnaissance. In these type of applications, the edge devices are deployed oftentimes in the field in drones or UAVs, which are performing various ISR tasks. And these are where the edge devices would have their sensor payloads, the cameras, possibly LiDAR, radar technology, embedded with the processor modules directly in the UAV or vehicle. In many of these applications, the drone or UAV is processing such a large amount of data that it needs to be able to offload this to a much higher power CPU and GPU solution, something that's just not feasible to fit in the aerial vehicle itself. In this case, the fog computing solution would be located at a ground base station or in a larger vehicle that would be more stationary. And in this location, all of the data that might be video data or radar data that would come down from the UAV would get further processed on the fog computing solution, such that it could harness much higher computing processing capabilities, but still keep this on-premise and on location and keep this communication locked between the edge device and the fog computing solution. In applications such as these, data security is of utmost importance. So having this close link between the edge and the fog and not having to pass any of this confidential or classified information up to the cloud is a huge advantage in these applications. When all of this information is processed, all of the real-time decisions have been made, the last final links of these last pieces of data that need to go to the cloud are not as critical, and they can already be disseminated from any classified information at that point before anything goes to the cloud. When looking at platforms and performance options, we've broken this down into server class, workstation class, and embedded class, where the embedded class would be your smallest footprint, lowest power, lowest cost of entry, and in platforms like the NVIDIA Jetson, you will see a very high performance per watt. And then when you move up to the workstation performance class, these are getting into higher wattage processors that are able to do more performance over the embedded, but do require a higher power footprint. And then moving all the way up to the server class, this is pretty inherent that these need to be much larger devices that will use a lot more power, but will give you the highest performance. And many of these can be used for training as well as inferencing these AI models. Typically, when we look at CPUs, we're talking about traditional processing models that CPUs consists of slightly fewer cores that are optimized for sequential serial processing, where these AI processing platforms have a massively parallel architecture consisting of thousands of smaller, more efficient cores designed for handling multiple tasks simultaneously, which is why in a lot of use cases for AI processing that the GPU is used for acceleration. And this can be done by offloading the compute intensive portions of the application over to the GPU, while the remainder of the code can still reside on the CPU. Looking at one of the latest NVIDIA GPU architectures to be available for edge processing or near edge processing is the Turing marker architecture. And this actually includes these Turing Tensor Cores. These Tensor Cores are specialized execution units designed specifically for performing the tensor matrix operations that are the core compute function used in deep learning. Similar to the previous generation, these Turing Tensor Cores provide tremendous speedups for matrix computation at the heart of deep learning neural network training and inferencing operations. These Turing GPUs include a new version of this Tensor Core, which is designed to be enhanced specifically for inferencing. When looking at this latest generation Turing architecture, they can be found within this discrete GPU in an embedded form factor, which is called MXM. And this MXM form factor comes in two different sizes, type B and type A. And the three different models range from the RTX 5000 at the highest end all the way down to the Quadro T1000 at the lower power end. One of the major improvements is the GDDR6 memory type that comes with this generation, as well as the ability to use over 3,000 cores on the RTX 5000 for CUDA-core technology. So when looking at building fog computing systems, marrying the x86 GPU in this embedded form factor, outside of a traditional server can be a difficult one. So one of the things that ConnectTech is showcasing here is the ability to leverage in computer on module technology for both the CPU and GPU and use an off-the-shelf carrier board to bridge both of these technologies together. So in this case, we're utilizing COM-Express technology for the x86 CPU to leverage the latest Intel CPU along with the NVIDIA MXM technology for the GPU. And again, these can be used to start with a development kit, which essentially takes a carrier board and puts sort of development thermals that can be used with sort of PC connectors that you can just fire this up in a lab environment and you're off and running. Whereas there's also subsystems available, which you can take these thermals and integrate this directly into your custom chassis. And then finally, in a fully turnkey fog compute system would involve all of the thermals, the mechanicals, and the chassis integrated around this so that the CPU, GPU, its custom carrier board, and its housing is all comprised in one unit. Companies that have their own internal engineering resources can develop these fog systems for their own needs. But in many cases, they need to talk to a hardware partner like ConnectTech to come up with a hardware strategy for them to go to market. And you're often having to weigh the level of customization versus your time to market. So we've broken this down into three major strategies here of either the quickest, fastest time to market would be going with a complete off-the-shelf solution. Something that we've shown in the last slide would be a carrier board married with a number of these computer on modules. This would be tested and verified and would be the most cost effective, but it may not fit all of your exact application needs. Another strategy would be going with a modified service. Now this sort of sits in the middle where essentially this would be taking an off-the-shelf carrier board and just making a few minor modifications to that. So possibly changing the form factor or a few connectors. And then lastly, the highest level of customization, which would be taking a fully turnkey design for a fog system and developing this exactly to your needs. But for this, it's definitely going to use the highest amount of development time and engineering expense. We hope you've enjoyed our introduction to fog computing today, and specifically with how we've been talking about how you can combine the latest x86 CPU and NVIDIA GPUs and how you can deploy those AI programs at the edge or near the edge. We'd be open to any questions you have, and we'd like to hear from you today.